Okay, continuing with homework problems. B. What is the linear speed of a child on a merry-go-round of radius 3 and angular velocity of 4 radians per second? So imagine, this will be hard to draw. A merry-go-round, if y'all have ever ridden on one of those, it's got the little horsey things. There's a terrible horse, and another one. These are not really horses, they're just some kind of creatures. And a child is riding on it. Okay, so this child is going, this is rotating, but there's also a linear speed occurring because we're moving in a circular motion. This is an example where we would have linear. So this one, it says angular velocity of 4 radians per second. We don't know anything about acceleration here. So maybe we're just moving in a uniform circular motion here around a circular path. So at any rate, so linear speed V equals R times omega, where this is our linear or our translational speed, like our normal displacement over time that we've thought of, but we're moving in a circular path with a radius. And then this is our angular velocity, our radians or angular displacement over time. Okay. So if we want linear speed here, we can just multiply these two. And that's going to give us 12, and it's going to be in meters per second. Radius is in meters, and then angular velocity is in radians per second, but we don't really use the radians in this answer. This really converts it to a length. So 12 meters per second. So this is a handy equation. Okay, there's several like this that we've looked at that they call, they're sometimes called bridge equations. All right, angular velocity of an object traveling in a circle of 0.75 meters radius with a linear speed. So here again, we're going to use that same equation, but we're solving for the angular velocity. So we're going to divide both sides by the radius. So we'll divide 3.5 meters per second by 0.75 meters. And then that's going to give us radians per second. Like the meters are going to cancel out. And we're going to come back to radians there. So 3.5 divided by 0.75 gives me 4.6 forever. So that looks like 4.7 to me. Radians per second. You don't have to write that. I just thought that would be appropriate. Angular acceleration of a ball that starts at rest and increases its angular velocity uniformly to 5 radians per second in 10 seconds. So this is an acceleration. This is where we want to think back to our kinematic equations, okay? And let's look at what are we given. We start at rest, so we start with an angular velocity initially of 0. We're increasing to 5, so that's going to be my final. Our time is 10, and we want acceleration. So I think this equation is the best one to use here because it's simple. It includes all the things we have and the thing we need. So I'll substitute in values. 5 equals 0 plus alpha is what we're looking for, times 10. 5 equals 10 alpha. Alpha is 5 over 10, or 0.5. And that's radians per second per second. Okay. See how we did that? So that's a one like the ones we practice where we do a, hang on a second. Okay, sorry. I think I was done talking about this one. I was just going to say this is one where we're using one of those kinematic equations. And so we need to write down our givens, what are we looking for, and then figure out which equation is the best one to use. So here it was the nice, simplest one. Okay, got another merry-go-round. Merry-go-rounds are a good, example of different types of acceleration and velocity for rotational motion. So here we've got a child pushing a merry-go-round with a constant force, okay? And the merry-go-round has this radius, and it's pushed from rest to an angular velocity of this, so it's speeding up. And it does that in 8 seconds. So we want its tangential acceleration. Okay, so, and this is something we need to go through more in class, but when you've got an object that's in a circular motion, okay, it's got a few different accelerations. It's in a circular motion, but it's speeding up or it's slowing down. It's got this tangential acceleration, which is like the linear version of acceleration. Because this is traveling a length as it turns, okay? It's also traveling angle, so and that's changing per second. So it's got an angular acceleration, and it's got a centripetal acceleration, which I think comes up in the next question. So we want tangential acceleration. This is linked to angular acceleration by another one of these bridge equations, okay? But before we can solve for it, we've got radius, but we don't have angular acceleration. So we've actually got to do another step first. We're given kind of the same type things as we were in the last problem. We've got an initial velocity, angular velocity of 0 because it's pushed from rest. We've got a final of 3. Okay. We've got a time of 8. We need this. So we can use this same equation. Final angular velocity equals initial angular velocity plus acceleration times time. So we've got 3 equals 0 plus 8 times alpha. So alpha is basically 3 over 8, which is 0.375. So then I can take this, put it over here, to get my tangential acceleration, my linear piece of the movement of this merry-go-round. I multiply my radius of 2.5 times my acceleration I just got of 0.375. And let's see what I get. 2.5 times 0.375 is 0.94. And it looks like that's one of our answer choices. So how fortuitous. And that's in meters per second, because I'm taking this angular acceleration and converting it, so to speak, to a linear acceleration by this relationship. This really starts back with the arc length and radius and angle relationship that we looked at the beginning of this unit. Okay, let's see if I have time to do one more. I think that I'll stop with that one, and then I should be able to get the final ones done in the last video.